Hello, my name is Jared Skeens and welcome to the Zoom room. Today we'd like to cover Statistics 1, Probability Part 3, the Probability Distribution Table. So what you've been doing in probability before is focusing on a particular probability, that is one pathway along a tree diagram. Or in the previous video, you learned about independent events, that is whether or not one part of the tree diagram is dependent or not on a previous part of the tree diagram. And you've also learned conditional probability, which again is focusing on a specific branch or outcome in the tree diagram. So what we want to do now is expand our probability to an overall view of a particular event, not just a specific outcome, but all the possible outcomes with respect to a specific event. And we can do this by filling out what's called a probability distribution table. In other words, how is the probability distributed throughout the possible outcomes? So what you're going to do is you're going to create a table that looks like this. You're going to have a little x on top, and you're going to have on the bottom this P of capital X equals little x. So the capital X is your variable, meaning it's what has the changing possible outcomes. And it is the event that you are analyzing in this particular question. So it's a specific aspect of the event that you are analyzing, and you want to look at all the ways that that one aspect of this event plays out. So the little x then is this top row. The bottom row is your probability that your event takes a particular value. So the little x are the possible values that can happen with respect to your event, the capital X. Okay? So when you read the question, the first thing you're going to look for is what is the capital X? What is the variable or event that you are analyzing? Then you're going to have to go through two mental, conceptual thinking processes. And the first one is you're going to have to be able to determine the possible values that that particular event can take. And you're going to list them in order from least to greatest in this top row. All the possible values that can come out of that event. Don't forget to consider the number 0. 0 is sometimes a possible outcome that students often forget. 0 is not always a possible outcome, but you should at least consider it. So the little x are those possible values. That's the first mental process that you have to be able to do. The second one is once you've decided those possible outcomes, you then need to be able to calculate each of their individual probabilities. In fact, sometimes Cambridge will ask a question prior to the distribution table for a particular probability, and that probability might be one of your boxes in the table. So this is what our main focus is going to be on in this particular video, is how do we read the problem, identify the variable, come up with our possible specific values that the event can take, and then figure out their individual probabilities. That's going to be our main focus. Then, since our information is in a little bit different format, we need to go back and revisit mean and variance. And here you see this capital E of X. This capital E of X is called expected mean. Now, the difference is this. When you calculated mean back in the first chapters or the first unit of statistics book, you had the data already physically present, and you just added up the values and divided by how many there were. That's how you calculate mean. Well, this is anticipating an outcome, meaning you don't have data yet. So it's an expected mean based on basically a probability chart. So your probability is in essence the same thing as your frequency, and like when you calculated mean from a frequency chart. So it's now called E of X, or expected mean, and it's the sum of your individual values times their probability. Again, probability is functioning similar to frequency. So that's how you're going to calculate mean from a probability distribution table. Then variance is going to follow this formula, the sum of the x squareds times their probabilities minus the mean squared. And again, this is very similar to the formula you learned for variance back in the beginning of the statistics book, but it's been modified again for probability distribution table. So instead of frequency, you now have probability. And of course, if you want to find standard deviation, you just square root the variance. So that doesn't change. Okay, so you have two new formulas, not really new concepts, just new ways of calculating it based on the information that you have available. And we want to now go into how do we do this probability distribution table. So let's start with our first question. Let me share the screen here. And in our first question, it says, at a fun fair, Amy pays $1 for 2 attempts to make a bell ring by shooting at it with a water pistol. If she makes the bell ring on her first attempt, she receives $3 and stops playing. This means that her overall, she has gained $2. So she shoots at the bell, and on her first shot, hits the bell, gets $3. She had paid $1, so she's now gained $2. If she makes the bell ring on the second attempt, she receives $1.50 and stops playing. This means that overall she has gained 50 cents. So she gets back $1.50, she gave $1, so she's now only gained 50 cents. If she does not make the bell ring in the 2 attempts, she loses the original $1. So her gain is actually a -1, or lost $1. The probability that Amy makes the bell ring on any attempt is 0.2, independent of any other attempt. So our first step here is show that the probability that Amy loses the original $1, meaning she misses the bell on both attempts, is 0.64. So we have to show that. Then it asks us to complete the probability distribution table here, to fill in the probability distribution table. And we need to also calculate Amy's expected gain. So let's go back to our board here and look at the first part. So in the first question, it asks us to show that if she loses the $1, that the probability is 0.64. And it says that her probability of hitting the bell on any particular shot with her water pistol is 0.2, meaning if it's 0.2 probability that she hits the bell, it's a 0.8 probability that she misses. And in order to lose the dollar, she has to miss twice. So what we're really looking for is the probability that she misses the bell both times. And so the probability of missing the bell once is 0.8 times the probability of missing the bell again is another 0.8. And so that's how we get our 0.64 as our probability of losing the dollar, okay? Now, the second part asks us to fill out a probability distribution table where our big X, that is the variable that we're analyzing, represents the gain, and it can also be loss, or in other words, what is the money outcome of this event. So what we want to do is we want to, in the little x, we want to list all the possible money outcomes that can happen. So we see that if she misses the bell on both attempts, that the money outcome ends up being she loses the dollar. So it's a -1. If she hits the bell in 2 attempts, she gets a gain of only 50 cents. Remember, she gets back $1.50, but she paid $1. So that's only a gain of 50 cents, so 0.50. And then if she hit the bell on the first shot, she gets a total of $3, but she paid $1, so that's a gain of $2. So these are the 3 possible money outcomes, and you should think your way through it. Think that, okay, if she misses both times, if she misses once, and if she doesn't miss and hits it on the first one, and you want to arrange them in order from least to greatest. So first you identify the variable. Then for your mental strategies, the first one is you need to identify all the possibilities here. Now our second one is to figure out how to get these probabilities. Now we already figured out this one here. It says miss twice, which means lose $1. So the 0.64 is already calculated in the previous one. So you want to keep in mind work you've already done. Now, if she hit the bell on the second shot, it means she missed the first shot. So it's the probability of a miss followed by a hit. So this would be a 0.8, which is the probability of missing the shot, followed by a 0.2, which is the probability of hitting the bell. So that's a 0.16. 0.16. And then we want to also look at the probability of her hitting the bell on the first shot, which we already saw in the information given that the probability of hitting it on any particular time is 0.2. Now, just to make sure, one thing you can do to make sure you have all of these possibilities is add up the probability and see if it comes up to 1. It needs to equal 1, which represents 100%. So 0.64 plus 0.16, so that's 6, 7, 4, and 6 make 10, so that's 0.8, and then 0.2 makes 1. So we know we have all the probabilities, which is a good indicator that you also have the possible specific values that it can take. Then in the third part, it asks us to find the expected mean. What is the average that you could expect if you play this game several times? So to find that, we take the sum of each specific outcome times its probability. Again, the probability is basically functioning as a frequency. If you have 100 games played, 64 games, you're going to lose $1. 16 games, you're going to hit it on the second try. And 20 games, you're going to hit it the first time. So it's basically like frequency table. So we sum that up. So what we get is a -1 times 0.64 plus 0.50 times 0.16 plus 2 times 0.2. So we're adding up, that's the summation sign, we're adding up the individual x values times their specific probability of occurring. We add that up, and you're going to see that this comes out to a negative 0.16. A negative 0.16 would be your expected average. So in other words, your risk of loss is greater than that promise of reward. So this probably is not the best game to play at the fun fair, since the average score is going to be a losing score. But anyway, that's how this works. Probability distribution, expected mean, and variance formulas. These are in your formula sheet. Okay, these are in your formula sheet so that you don't really have to memorize them, but you should become comfortable using them, and you should know where they're at in your formula sheet. So for quick reference, if you forget, you can pull it up. Now, let's go on to the second example, and I have set up examples that are quite different from each other as far as the problem goes, but of course, this part is basically the same. Okay, here's our second question, and what we have here says, Andy has 4 red socks and 8 black socks in his drawer. He takes 2 socks at random from his drawer. Find the probability that the socks taken are of different colors. That's the first one, the probability that they're different colors. And the second one says the random variable x is the number of red socks taken. So drop the probability distribution table for x. And then in the third one, find e of x, meaning find the expected mean. So that's the questions for this one. So let's go back to our board here. I wrote the information up here. There are 4 red socks, 8 black socks, and we're going to draw or take 2 of the socks at random. So the first part says, what is the probability that they're a different color? But you're only taking 2 socks, drawing 2 socks. So either you get red, 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 blue, blue, sorry, not red or blue, red, 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 black, black, red, or black, black, right? So if you want different colors, it's either going to be red first, followed by a blue or black, or it's going to be the black first, followed by the red. So that's what we want to calculate here. So if the red is first, that's 4 out of 12 times, and then if the black is next, it's now 8 out of 11. Don't forget you've taken a sock out, so it reduces the total number of socks. But since you took red first, you still have all 8 black. Plus, because there's 2 ways, there are 2 different pathways that end up having different colored socks. So the pathways are like your horizontal tree diagram, and then the outcomes are looking at it vertically, so we add them. So if the black is first, it's 8 out of 12 times the red would then be 4 out of 11. And if you calculate that all there together, you're going to get 16 out of 33. So that is our first answer to the probability question. Now we're asked to create a probability distribution table for the event dealing with how many red socks that are drawn, that could be drawn in this event. So again, remember I said consider the possibility of 0. Don't forget the possibility of 0. So if you have 4 red socks and 8 black socks and you're only taking 2, it's possible that both of those socks are black, meaning that you can have a 0 as an outcome for the number of red socks. As we see with this, you could also have 1 red sock, 1 red and 1 black in either order. It doesn't matter, you end up with 1 red. Our variable is how many red socks we end up with. So we could end up with no red socks, we could end up with 1, or it is possible because there are 4 of them in the mix, we could both of them end up being red. So here are the possible values that this variable can take. There can be none, 1, or 2. So that was the first mental thing to do, is figure out the possible values. Now we need to figure out the probability for each. Of course, we want to look back here. This 16/33 is for 1 red sock. So that's already part of our work right here. 16/33. So what if there are no red socks? Well, that would be, let me do it down here off to the side. If the first one was black, that would be 8 out of 12. And then if the second one was also black, then that would be 7 out of 11. So if you do 8 out of 12, and then you do 7 times 11, you're going to end up with 14/33. 14/33. And then for this one here, 2 reds would be a 4 out of 12 times a possible 3 out of 11. So red on the first one, red on the second one, and that's going to give you, it's going to reduce to 3/33. You should do all of these separately and then check to make sure they add up to 1. So 16 and 14 make 30, plus 3 is 33/33. It does add up to 1. So that should make you feel good that you've accounted for all the possible values that X can take, and that you've probably correctly calculated the probabilities for each as well. So that's the probability distribution table. Now that you have that filled, now we can find the expected mean. In other words, if you were to do this over and over again, what would be the average number of red socks that you would expect to get from 2 draws? So to do this, again, we do the summation of each X value times its probability. So 0 times 14/33, and that's just 0. It's okay. It's going to cancel or just disappears. Don't worry about it. Plus 1 times 16/33 plus 2 times 3/33. So you can see that you have 16, and then this was 2 times 3. So 16 and 6 are 22/33, which reduces down to 2/3. Now remember, mean is an average. It's not a specific It's not an integer, so it's okay. It means that the average is going to be less than 1. If you notice this chart, it's skewed in the positive direction, meaning the bulk of your data is over here and the tail of it is going off in the positive direction. It's skewed in the positive direction, which means all your information is kind of shifted here on the left side. And so if you look at these three, you might think your average is 1 because there's only 3 of them, so the average is the middle. But because the probability is not symmetrical, the average is shifted to the left and it's actually 2/3. So you're going to average less than 1 red sock if you do this multiple times, right? So that's how that works, how you interpret the information, and hope you're starting to get the hang of this. Let's look at one more example together. Okay, let's look at our last example here. Now we have spinners, a fair, and when it says fair, it means you have an equal chance of getting any particular value on the spinner. So if you see the words fair, not biased, or unbiased, it means you have equal opportunity for all of the outcomes. If it says biased, then it has to provide for you the different probabilities of getting the different outcomes. So a fair means not biased, so you have equal chance of getting any particular number here. So a fair red spinner has 4 sides numbered 1, 2, 3, and 3. And then a fair blue spinner also has 3 sides numbered -1, 0, and 2. When a spinner is spun, the score is the number on the side on which it lands. The spinners are spun at the same time. The random variable x denotes the score on the red spinner minus the score on the blue spinner. Draw up a probability distribution table for x. So that's going to be our first task. A little bit more challenging than the previous examples. So we'll make our probability distribution table. Then it says find var x, or in other words, find the variance for this particular probability distribution table. Okay, so let's go back to our board here. And I've written the information up here. So the red spinner has 4 numbers, 1, 2, 3, 3. That means the 3 actually has a 50% chance here because it's 2 of the 4 items. And then the blue spinner has -1, 0, and 2. And our event that we're looking at is the score when you take the red spinner value minus the blue spinner value. And we want to create a probability distribution table. And of course, at first, you don't know how many values possibly could be, outcomes. So you really have to think carefully through this first row. That first conceptual is very important, because if you miss a possible value, then you're going to only calculate some of the probabilities. Of course, if you add them up and it doesn't equal 1, you did something wrong. You missed something up here. So let's start with the minimum value. The minimum value, since you're subtracting, is going to be the smallest value here minus the biggest value over here. The smallest value here minus the biggest value over here is going to give your lowest possible outcome. So a 1 minus a 2 gives us a -1. So we have a -1 as our first value here. And then we can also, then you want to think, okay, what's the next number after -1? It's 0. Is it possible to get a 0? Well, 1 minus 0, well, that's 1. 1 minus 2, no, that's negative 1. 1 minus negative 1, no, that's 2. You can't get a 0 from this one, but you can get a 0 from this one. 2 minus 2. So it is possible to get a 0. How about 1? Yeah, 1 minus 0. We already see that one, 1. What about a 2? Yeah, 2 minus 0 is 2, or even 1 minus the negative 1 is 2. So there's a couple of ways of getting a 2. What about a 3? 3 minus 0, yep. What about a 4? What about 3 minus a negative 1? When you minus a negative 1 means you're actually adding 1. So here we end up with 6 different possible outcomes for this particular event. So in the previous ones, we only had 3. On this one, you have 6. So you really want to think carefully from your lowest possible one all the way up to the highest possible one. Think it through, make sure you have all of them. Again, we can double check it once we have our probabilities. So how do we go about getting the probability? Well, first, let's look at the probability of a combination here. So the probability of getting any particular value of the red is 1 out of 4. And the particular probability of getting any one of the blues is a 1 out of 3. Okay, so that means that for a particular red and a particular blue, that's going to give us a 1 out of 12, meaning there are 12 different combinations that we can come up with. So what I'm looking for is, what is our bottom number? What is our denominator going to be when we're dealing with this many items? So 1 out of 4 times 1 out of 3 means there's 12 combinations that we need to come up with. So to get a negative 1 is only a 1 and a 2. There's only one way of doing that. So that's a 1/12. To get a 0, well, that's 2 minus 2. If we take 3 minus a negative 1, that goes to 4. If we do 1 minus 2, the only way of getting a 0 here is just the 2 minus the 2. So again, that's also only one way of getting it. So that's a 1/12. One number from here, one number from there. How about getting a 1? Well, we can get a 1 by doing 1 minus 0. We can also get a 1 by doing 3 minus 2. And also this 3 minus 2. So since there are 2 3s, we got to count it twice. So there's 3 different ways that we can come up with a 1. So that's 3 out of 12. Notice I am not reducing it to 1/4. I like to see all the same denominator. It makes it easier to calculate at the end if you arrive at 1. So usually the Cambridge mark scheme will accept it without it being reduced, or if you want to, you can wait until you're sure you did it right, then you can reduce them, or if you wanted to, you could put a 1/4 down here below it. You can do it like that as well. So how many ways of there are getting a 2? Well, 2 minus 0, 1 minus negative 1. So there's 2 different ways of getting a 2. So we have 2 out of 12 for that. How about of getting a 3? Well, obviously 3 minus 0 and 3 minus 0, that's 2 ways. And 2 minus a negative 1 also gives you 3. So there's 3 ways for that. And to get a 4 can be 3 minus negative 1, or this 3 minus negative 1. There's 2 ways of doing that. So if you want to change this to 1/6, that one is, 1/4. And 1/6, you can if you want to. But before you do that, you want to check, maybe we missed a particular combination. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of 12. Yes, it adds up to 1. That's a very good sign that you've come up with all the possible specific values and you've come up with the right probabilities. At least it's a high chance that you've done it correctly. So this then is your probability distribution table. Now we want to come up with the variance. But in order to do variance, you have to have the expected mean. So let's do the expected mean first. So the expected mean is multiplying these all together. So we get, and adding them up. So we get a negative 1/12 plus a 0 plus a 3/12 plus 4/12 plus a 9/12 plus an 8/12. And what does this come up to? Well, 9 and 8, 17. 20, 24 minus 1 is 23/12. So that's our expected mean. Now we can go through and do the variance part. So the variance part, you square the x and then multiply. So squaring a negative 1 gives you positive 1 times 1/12 plus 0. When you square 0, it's still 0. 1 squared is 1. 2 squared is 4 times 2/12 is 8/12. 3 squared is 9 times 3 is 27/12. And 4 squared is 16 times 2 is 32/12 minus our 23/12 squared. Okay? So when you calculate all of this, you're going to end up with 71/12, all of this in here, put it down here, 71/12 minus our 23/12 squared, and you calculate that and it will come up with 323/144. Kind of an ugly number. Let me show it so that you can see it here. 323/1, that's a 144, not a 149. 144. Kind of an ugly number, but you can check the mark scheme. It's correct. So don't panic if it doesn't really look good. Remember, it's variance, which is a measure of spread. So when you're talking about spread, you don't really expect nice numbers. So don't worry about that. So this one was a little more tricky because there's a lot more variations in how these numbers combine. And so you really got to think carefully through it. Calculating the probability wasn't so difficult as long as you have the right number of combinations that give you the specific outcome. And as long as that is correct, again, double check to make sure your probability adds up to 1. That's key. As long as that's correct, your variance is just a matter, or mean is just a matter of following the formula. Just be careful that you follow it correctly. Make sure you do exponents first, then multiplication, then add them up, minus the mean squared, and these should be easy points for you to get. So that's how probability distribution works. In the next unit, we'll be looking at more difficult distributions that require formulas to figuring them out. These distributions we can do manually because the data set is small enough for us to work with that we can do it manually. So a lot of exciting things ahead, but I hope this helps you with this particular lesson. Again, thank you for joining me, and I look forward to seeing you next time.